Auto white balance plays an important role in rendering the final colors in a photograph. Most auto white balance modules assume a single light source is present per scene. However, real scenes often have mixed lighting conditions. Performing single illuminant auto white balance on scenes with multiple illuminations often produces unsatisfactory results. Here we show a typical example of a scene captured with a mixed lighting condition. Because the captured scene has two different light sources, an outdoor light on the right and an indoor light on the left, traditional white balance correction results in either a reddish tint in the final rendered image, as the auto white balance only corrected the outdoor lighting, or a bluish tint in the final image because the white balance corrected the indoor lighting. Here we show our auto white balance result that considers both lighting conditions. In order to understand why traditional auto white balance is limited to a single illuminant per scene, we need to first understand how white balance correction is applied on a camera. White balance is applied to the raw sensor image by first estimating a single illuminant RGB vector that represents the global color tint in the raw image. Afterwards, a single diagonal correction matrix is applied to all colors in the raw image. After white balance is performed, additional color rendering routines in the form of tone maps and 3D lookup tables are applied to produce the final standard RGB or sRGB image. In a departure from conventional auto white balance, our method does not require luminant estimation, as is the case with conventional auto white balance. Instead, our method proposes to render the capture scene with a fixed white balance setting, for example daylight. We then downsample this initial sRGB image to speed up processing. Next, we downsample the raw image and process it through the camera with a number of fixed white balance settings, for example, incandescent and fluorescent. Given this set of small sRGB images with different white balances applied, our method learns to estimate weighting maps that are upscaled through a post-processing step, then used to blend the multiple white balance images to produce the final corrected image. Our hypothesis is that the final corrected white balance can be generated by linearly blending among the different white balance settings. By observing the same scene colors under a fixed number of white balance settings, our deep neural network can get good cues about the proper blending weights. We apply our network to compute the weights for each image, then combine the images to produce the final output. See our paper for more details. To train our network, we use the rendered white balance dataset that includes over 60,000 single illuminant images. Each image was rendered from a raw image to sRGB with different white balance settings. In addition, each image is associated with the ground truth image with properly white balanced colors. We train our network on patches extracted from training data in the rendered white balance dataset. We feed our network with the same patch rendered with different white balance settings. The network is tasked to predict the weighting maps to be applied to those patches. Then we compare the output with the ground truth patch to compute our losses. By training on patches of single illuminant scenes, and given the fact that our network is fully convolutional, we can deal with mixed illuminant scenes by convolving over the image to get the mixed illuminant weighting maps. We've evaluated our method on the single illuminant Cube Plus dataset to validate our hypothesis. We also provide several ablation studies with different training settings, including the number of fixed white balance settings applied to the downsample raw images. Our method achieves promising results compared to state-of-the-art white balance correction methods. In addition, we generated a testing set that includes 150 images with mixed lighting conditions. We begin with 3D scene models and use 3D Studio Max to render the same scene with different white balance settings as shown here, represented by different white balance color temperatures. Here we show qualitative results that show the camera's output, the correction of the camera's output using two state-of-the-art white balance editing methods, and the output generated using our method. Our method fails in some cases due to inaccurate estimation of the weight maps. However, as our method works by blending images based on predefined white balance settings, our failure cases often produce results similar to traditional single illuminant methods. In summary, we have presented an auto white balance method targeting mixed illuminant scenes. Our method works by locally blending between a fixed set of predefined white balanced images. As part of our contribution, we have generated a synthetic test set of mixed illuminant scenes with pixel-wise ground truth. Thank you for watching.